Hi, my name is Bianca, and first we're going to be talking about resting potential. So first with resting potential, I wanted to show a neuron, and these large proteins inside of the neuron are the anions. So the large organic anions are negatively charged. Even though there's positive molecules inside the neuron, these anions are so negative and so big that it makes the inside of the cell negatively charged and the outside is positively charged. So to go into a model here, I have kind of a key to show you that chlorine is the red, sodium green, and potassium yellow. So extracellular space means it's outside of the cell, and this is representing the membrane of the neuron. And the intracellular space is inside of the cell. So inside the cell, potassium is positive, but still remember that the anions, large proteins, make the inside of the cell negatively charged. And the outside of the cell is positively charged. And you can see sodium, chlorine take up mostly that space. So in this membrane, there are ion channels, and they are selectively permeable. So on the inside of the cell, there's a lot of potassium, but there are leaky cells. So sometimes potassium can leak out and sodium can come into the cell. So we'll say a couple of those are leaking out and sodium's coming in here. So what happens here is diffusion. So what happens when diffusion works is when a high concentration of something goes to a lower concentration. So when those potassiums that are intracellular were moving outside the cell, it was going to a lower gradient, a lower concentration. So that is diffusion, and also same with potassium. Next, we'll look at the electrostatic pressure, and that's the forces of charge will work together or push away. So we have a negative charge inside the cell. So that's going to push chlorine away. So all these red chlorines are going to want to go away from the inside of the cell. Versus the sodium, the green, this is negatively charged. The sodium is positive. They want to come together. So sodium will come into the cell. And next we will look at the sodium transporter, or the sodium potassium transporter. So this is what we drew here in the middle. That is a special protein that will only allow 3 sodium out. So from in here, 3 sodiums are going to be put in here, and they're going to be taken outside of the cell. Now, for every 3 sodiums that go outside of the cell, 2 potassiums are going to go in. So this protein works via ATP, and a lot of energy actually happens even though the cell is resting. And that explains the resting potential, and we went over these definitions. So next we're going to look at action potential. So first, for action potential, I wanted to show a picture of this neuron in the axon. So on the axon are these myelin sheaths, and each one of these is the myelin sheaths. And then in between this little gap is the node of Ranvier. So we're going to keep that in mind here, because it can be pretty important to remember that the myelinated neurons are covered with the myelin sheath. So that's what it is on top of it. And that allows the electrical signal to travel faster down the axon. So once the electrical stimulation is here, a signal happens and it travels down the axon. And the only place between the myelin sheath, the node of Ranvier, is activated and makes actual action potential. So when that action potential starts, it goes, kind of dances over here. So sorry, I keep pushing it away. When an action potential leaps or goes along a myelinated axon from one node, so one node to another, it increases the velocity of the action, or it keeps increasing the velocity of the action potential. And that is explained through saltatory conduction. Saltatory conduction. So with that, I just want to use this model to explain the rate law. The rate law is when different stimulus intensities, so you can shock it a little or shock it a lot, it wouldn't change the strength of the action potential. And we'll visit this graph in a second and you'll see why. But it does change the rate at which the axon fires. So it wouldn't change the intensity because we got to hit a certain point and it will stay that certain point no matter what. But it will change the rate at which it's fired. So we're going to go over here and look at this guy. So what you'll see here is different stimulation, different voltages of the stimulation. But once you hit a certain point, you hit the threshold of excitation. So that's the value of the membrane potential that must be reached to produce an action potential. So that just means when a neuron has enough stimulation, it hits a threshold of excitation. Which also brings us to the all or nothing law. So that says that a stimulus must cross the threshold of excitation for the potential to happen. So if a stimulus doesn't hit that point, which is about negative 55 millivolts, nothing happens because there's too weak of a stimulus. But once it hits that threshold, it triggers all voltage-gated ion channels. So to explain that, we are going to go to this guy. So when stimulation happens and that threshold is reached, for a little bit we're going to hit a point of depolarization. So at depolarization, that sodium ion channel opens. So when that opens, all the little sodium guys are coming in here. So when that happens, that potentially flips the cell. So down here is no longer negative. Instead, the intracellular is positive and the extracellular is negative. So what we want to see then, it causes the positive to leak in. Now, shortly after that happens, we'll see repolarization. So repolarization is when the potassium channel will open. And these are voltage-gated ion gates because something has to happen. Some type of voltage has to happen. So the sodium will close in repolarization and the potassium will open. So the potassiums will go back out. Now, what happens after that, and you can see from this graph, is hyperpolarization happens. So that's when the cell kind of overdoes itself and has to balance itself out. So it kind of overdoes, goes back down, and then it has to balance itself out. And it does that via the sodium-potassium transporter. So that guy will start doing his thing, pumping the sodium back in and the other ions that are supposed to be the potassium back down. So it will balance again, and then you'll see it goes back to the resting potential until the next stimulation. So thank you, and I hope that clarifies.